privilege to travel again and together in a room. I think that's something that we as a scientific community we've missed out on some things, but we've also become really good at collaborating without having to travel. And so I think it's delightful to be speaking in this virtual forum to everybody in this room and outside. So today I'm going to be talking about a number of operational models, research models that COM6 is using. But really the subtext in all of this is very much in alignment with Andy's talk about the importance of community modeling and how community modeling enables us to do these things, make much more rapid progress, and an open invitation to broad engagement. And although I'm speaking specifically about MOM6, we could have put together a very similar talk about many of the other components that NOAA, the US's National Oceanic and Atmospheric Administration, uses to meet its mission needs, but also uses to engage people in the research community. So a few words about MOM6 for those of you who don't know. It is very much a community ocean model. The thing that makes it a little bit special is it's based on this idea of using vertical Lagrangian remapping for the vertical coordinates. So you can use the same numerics and very transparently use them with a vertical coordinate that's adapted to the specific application that you're using. Critically, this introduces a couple of things. First, there's no vertical CFL limit, so you can have vertical resolution. This is fine as you like it to be. It's also, from the global climate perspective, particularly good at reducing diacritical mixing in some coordinates. And it has a number of efficiencies for biogeochemistry and passive tracers that I'll discuss momentarily. We have a whole lot of new capabilities under development. These are just a few of them. I'll talk about them much more in my talk on Thursday. But these are coming from GFDL, they're coming from NCAR, they're coming from NASA, they're coming from collaborators all around the world. And each of those are immediately available to other people to take a look at, to evaluate, to use. And so critically for the success of MOM6 is this spirit of community open development with a very deliberate software design, but an open engagement with users and an open pathways to encourage people to contribute. And when I get to the end, I'll highlight a couple of examples of how that has worked. Now, the vertical Lagrangian remapping method is relatively straightforward. These are the shallow water equations, but you can break this up into essentially the stacked shallow water equations where the vertical coordinate moves, and then we will periodically remap it to your target coordinate. So this is an example of a side view of a descending dense plume that's rolling up. But this is before we've done the remapping into a z coordinate. And so you can see the continuity equation displaces the interfaces, but then we'll remap it, in this case, back to the z coordinate or to whatever coordinate you want. If it's a purely adiabatic model and you use, say, an isopycnal coordinate, there's no remapping needed. The model basically takes into account the vertical velocities via the movement of the coordinate surface. This has a number of critical advantages. First, it offers flexible vertical coordinates, as I mentioned, but in this case, tracer advection is not required to represent gravity waves. And so we're able to use the model with 4 distinct time-stepping cycles. These are the first two are pretty common to ocean models, the rapid external gravity waves, internal dynamics. But when it comes to the tracers, we're able to use a much longer tracer time step that's not constrained by a horizontal CFL limit. And critically, as we look at models that are going to be using Earth system models with lots and lots of tracers, we believe we're going to be able to hold the tracer time step, this much longer time scale, than you would need to use, especially as you push to high resolution. So this is enabling Earth system modeling through some clever numerics, and this is one of the key pieces that has led to fairly widespread adoption of MOM6 in the US. The second is we've been able to use this to make some really nice models. This is the sea surface vorticity from our CM4 coupled climate model that we created for CMIP6. I love this movie. I can watch it all day. It kind of illustrates the extreme richness of the system. So you see all the dynamics in the ocean, but you also see the imprint of the coupled system. You'll see hurricanes zipping through here in the ocean vorticity, the rapid things moving away from the tropics up towards mid-latitudes. But critically, not only are we pushing higher resolution with better verisimilitude, but we're also able to reduce the RMS errors. In other words, we're less dependent on the use of the subtracting off the control run to say things about how climate systems work. In other words, we're less dependent on the critical assumption of linearity as we make our climate projections. And a lot of this has to do with the vertical coordinate. So in this case, we're using a hybrid vertical coordinate, holding density surfaces in the interior, depth surfaces at the surface. And for comparison, these two models are identical except for the vertical coordinate. This one's remapped to depth surfaces, this to this hybrid surface. And what we're seeing here, this is a Bloom-Miller diagram of time, and the horizontal mean temperature anomalies is the pre-industrial control run as a function of depth. This drift, this warm drift, is very typical of other models of this resolution. By going to the hybrid vertical coordinate, we're able to dramatically reduce that interior ocean drift. And we were able to also replicate some of this nice behavior in a lower resolution model where we add parameterizations of the eddies. So this was the basis for a lot of the subsequent development, where people looked at it and said, look, you have lower drift, that's very beneficial for other applications of climate models. To the point where today, there are 4 distinct major efforts going on within NOAA to make use of these capabilities of MOM6 to meet different parts of NOAA's mission, ranging from operational weather forecasting, seasonal forecasting, or all the way to the management of fisheries and marine ecosystems in the face of a changing climate. So I'm going to step back a little bit from MOM6 and talk about the new unified forecast system that the US's National Weather Service is putting together, and the emphasis that this is placing on community open development, and community access, and community engagement as kind of the strategy for how these critical operational forecasts are going to be improved. So if we go back about 5 or 6 years, the forecast system that was being used was this kind of elaborate quilt of dozens of specialized models, many of them based on different codes, each of which had been kind of gradually evolved and adapted over time, but to the point where a number of the underlying capabilities were several decades behind what was being used in the operational, in the research communities, and each was supported by an increasingly narrow set of expertise. And there was kind of a realization that this had led to a lag in the rate of improvements in the operational systems relative to what was being done in other places. And more critically, that the US's very large, very active research community wasn't being effectively engaged in helping to translate our improved understanding into actual improvements in the forecast as effectively as we could. And so the strategy here, kind of thinking about this, was to say, okay, let's step back, let's figure out what we need to do to engage the community, try to reuse similar tools for specialized for the specific operational uses, but reuse the same community tools again and again in specific configurations. So the idea was that came forward is that the specific community codes would be identified, and each of these would then be applied in specialized, adapted to the specific applications. But critically, each of these is based on its own community, has an authoritative repository. Moreover, the licensing on each of these is being or is being adjusted to follow basically a public domain sort of approach. So everything I do as a US employee is in the public domain in the US. The licensing that's going to be applied is Creative Commons 0 or something philosophically equivalent to that, so that what we do is made available to the people of the world. And this is coming from Congress, and this is coming from the highest levels, but it's also something that has really strong buy-in from the scientific community. And something that was really pioneered in particular by MOM6 and the WaveWatch 3 models, that is now being propagated to all of the other components that are being used to create the unified forecast system. Within the unified forecast system, there are three major components that are going to be using MOP6. One of them is a real-time, high-resolution ocean state forecast system. And this is using MOP6, the data atmosphere, and the CICD CIS model. The second is the operational hurricane forecast system, the fully coupled forecast. And this is also using MOP6 and WaveWatch 3, but now with a high-resolution atmosphere. And then the third one is the seasonal to interannual forecast system used to forecast things like El Nino, the Madden-Julian oscillation. And this is also based on MOP6. Each of those are sharing components. In many cases, they weren't sharing them before. So advances in one lead to advances in the others. These are all being coupled together using the CMIPS mediator. This is a NOAA compliant mediator, very much analogous, I believe, to the one that's being used in ACCESS. But which each of these components that can then be turned on or turned off. In this particular case, this is the full global coupled model, which is being adapted for three different time scales based on a common root. And that common root is derived directly from the CMIP GFDL CM4 model, the one that I showed in animation a few minutes before. The result of this is that we're actually seeing significant improvements in the forecast skill of the model. In the top left, this is the sea surface anomaly in the Nino 3-4 region. The existing system, this is one particular case in 2015. The blue line is the existing system, the black is the observed. The new system, by pulling together the best that was available in the community and engaging with the community, led to a very significant improvement in the forecast skill of the system on timescales out. I think this one was a June initialization, so out something like 6 or 7 months. And so we're really quite pleased with that. There are still some things that could be improved. One of the things in particular is noted that there's this persistent warm bias in the eastern tropical Pacific, and if you look into that, that's related to the structure of the equatorial undercurrent. In this case, this is a common bias that occurred in the forecast system. We're also seeing something similar in related coupled models, and further investigation is suggesting that some of the details of the ocean's viscosity at the equator that is leading to this common bias, and so we were able to fix it in the coupled model, and that's something that's being communicated to the forecast model. So the fact that you have these two different applications, one of them is a seasonal forecast, the other one is a global coupled model for centennial forecast, is kind of a demonstration of the value of keeping closely coordinated and close comparison across common components. The other high-resolution forecast system that's being adopted has been using HICOM for some years. This is run at 12th degree resolution. It's used for search and rescue, say where are the eddies, various other purposes. These are equivalent MOP6 and HICOM configurations that are being used. And close comparison between the two reveals there are a lot of similarities, but also some points of difference. HICOM is actually being a part of the MOP6 consortium. So the developments that have been taking place independently in HICOM, we've been working with Alan Wolcott and our Chasquet to figure out where they differ, why, and how to come up with a system that is kind of the best of the best. And then this exact thing is being deployed operationally by NOAA for the high-resolution forecast. So again, we have this kind of building of the community, this increasingly tight exchange of ideas is leading to improvements across space and timescales for NOAA. Now we're also doing something quite similar for a seasonal prediction that goes on seasonal to decadal timescales. This is a little bit different than the operational system in that it doesn't run 24/7 in real time, it's run once a month, and you're able to wait until some of the data quality control has been improved. But we're using the same ocean models, in some cases at lower resolution. We've demonstrating the objectives of this project, both to make predictions as part of the North American multi-model ensemble, but also using exactly the same seamless system to do projections out to several decades. And so we are able to use this set up with a variety of different resolutions. You're able to select a resolution that's adapted to the cost and the timescale of a particular application. These are all closely related. This is the ocean configuration from that quarter degree that I showed. These other ones are low resolution versions of the same thing, but by selecting configurations that reflect the CPU cost of the particular timescales, we're able to identify improvements that carry over from one resolution to another. And so this is one example of predictability research using this component in a fully coupled system. This is the predictability of atmospheric river events 9 months in advance. And for those of us in the US, the supply of water by these atmospheric rivers on these timescales is a really great value because it tells you how you want to manage your reservoirs. Do you want to have them empty? Are you expecting there's going to be a flooding potential as there was this last year? Or are you expecting drought? So you want to hoard water and in preparation for potentially dry year. So this is demonstrating that this kind of common approach across timescales is contributing to significant advances in operational usable research. But at the same time, you can take the same model, which you've verified and validated by close comparison with the data, and apply to questions of, in this case, what happens to the intensity and frequency of atmospheric rivers as a result of global warming later in the century. So the two are, again, mutually supporting each other. In this case, the validation happens with the operations, but then it also gives us insight into how the planet will evolve going forward. At the same time, we're taking this CM4 model, and this is a basis for higher resolution versions of the same thing to do a better job of capturing the eddies. This may be a little bit of a gratuitous illustration as the planet spins, and you see that this works really well both in North America and in Australia. I'll have more to say about that later today. But I think this, again, the fact that you're using the same tools, users who become proficient using one are able to use that same expertise for others is a really great virtue of this kind of shared interoperating system. And so the final set of applications that I'm going to talk about are the use of exactly the same modeling system, but now in regional configurations. Within the US, there's a major new effort to try to use these regional models to estimate what the effects of climate change will be on marine ecosystems. This is being done in collaboration with our National Marine Fisheries Service so that they can figure out how to adapt their management strategies towards accommodating the fact that the information we have from the past is no longer going to be as valid in the face of climate change as species shift their range, often poleward and deeper, or change the timing. And so this is basically a transformation pulling together the physical climate community and the community that manages marine ecosystems. In this case, we have separate regional configurations with open boundaries for the US East Coast, for the Arctic, for the West Coast of the US, and there are a handful of other configurations that are being developed and deployed as well, both in the US and with partners in Korea and in Brazil. In Brazil, the application here is the identification of oil spills. A couple of years ago, there was an oil spill that led to oil showing up on the beaches of Rio de Janeiro during Christmas. And the response is to develop a comprehensive system to identify, monitor, and backtrack to figure out which ships were responsible for those oil spills. But here in Australia, one of the emerging developments is in the context of the Center of Excellence for Weather of the 21st Century, where one of these configurations, yet to be completely fleshed out, is going to be used for fully coupled forecasts. So within NOAA, we're using this as part of something called the Climate Ecosystem Fisheries Initiative. This is an example kind of zoomed into a sub-portion of the domain, where we're looking at the amplitude of the tidal velocities, the implied vertical mixing, both from the tides and also from the atmospheric forcing, and how that relates to surface chlorophyll in July. This is validated for today's world, but the fact that we're capturing all of the physics across this wide range of scales is kind of establishing the credibility, so that when we look at how this will evolve going into the future, including changes to the tides, changes, of course, in stratification, this will give us we believe, some credibility in projecting what we need to do to manage these changes. And this is another example now on the West Coast, showing the simulation of the chlorophyll in the California current system. Now this is something that's challenging to resolve in global models because of the very small spatial scales involved. But by using a regional model, you can downscale, and you can use this to project how this will change. But the fact that this is exactly the same set of software, same set of tools as we're using throughout, means that somebody who has gained experience with one set of applications is able to apply it to others. And moreover, any developments that are made here are applicable across the space and time scales. And one demonstration of this is very recent. So this is a Northwest Pacific regional configuration that's been developed in collaboration with some of our colleagues at the Korean Institute for Science and Technology, where they adapted an existing MOM5 run that they've been using operationally for some years to MOM6, but they used now the new tidal capabilities and boundary conditions from the Northwest Atlantic, adapted it to the Northwest Pacific, and now this is being used to study the evolving tidal amplitudes and mixing in the waters around the Korean Peninsula. This is done by a graduate student, 2 months, pulling in other parts of the community. And this is now something where these capabilities are available through the community. It's a way of empowering people to contribute, to get up to speed quickly. I want to say a few words about open development in MOM6, and this is very much in line with the spirit of what Andy said earlier. So everything that we do on MOM6 is completely transparent. There are no essentially barriers to collaboration. We structured it in this hierarchical way so that if you have a user who's developing some new idea, they would first send it into one of these kind of regional nodes for evaluation. Once it's been reviewed at this level, this is something that then can be broadcast to the whole consortium with coordination between the various branches. Now we have 8 different groups that are kind of managing things, and essentially each one of them is a group of people with common interests, but also a common set of regression tests that they carry out. So we have what we call the Hippocratic principle of ocean modeling, first do no harm. And so nobody changes anybody else's answers. Everything we do is done by consensus. So if somebody has a good idea that comes into one of these hubs, try it out, make sure that it works at that hub. Once it's working there, then we try it with the whole community, we run it across the regressions. If nobody's answers change, then it comes in. If the answers change, we go back and figure out why, and we figure out how to restructure the code, both to accommodate the new contributions and to make sure that they're not disrupting the activities that other people are going on. The important part of this, though, we rely heavily on a set of self-consistency tests. So if you as a graduate student have an idea that you want to try out, you can figure out if it's going to pass, very likely, before you even ask anybody. so that you can get an immediate feedback. And these are self-consistency across things like processor times and restarts, but also dimensional consistency. And these are all automated tests. Between the two of them, this has worked out to be a very effective system using GitHub, as Andy noted. And we're now at a point where we have, we've had more than 48 people contribute more than 100 lines of code. We have 8 major groups working on it. So developments that are happening at NCAR are made available essentially either immediately or if you wait for the synchronization of the main branch after a few months to GFDL or POSIMA. If you have a contribution here that you wanted to make, the first place to go is say to whichever of these groups you're mostly aligned with to test it out for review. But it's a way for the community to become engaged. And we have some wonderful examples of graduate students, new people making contributions. We recently had one graduate student who identified that we were multiplying by the von Karman constant twice in a particular parameterization, came in to review, we reviewed it, we propagated it. They spotted something that had been there for 10 years. Some bug, hard to spot, but made an important contribution. We've had graduate students making contributions of new parameterizations. So for instance, Abigail Bodner revised how we did our parameterization of sub-mesoscale restratification, replacing a previously fixed dimensional constant with something based in theory. That's something that came in by one of these branches, it's tested out, and within weeks it's available to all the branches to be able to use. So this is an open invitation to please contribute. You have a space, you have a place, you have a way to contribute what you're doing. And by doing this, it's a way to both allow everybody to benefit from each other's work, but also to propagate the great work that people are doing, make it available to the rest of the world in real time, make it usable by the rest of the community in real time. And I think this, even more than the specific applications, is really at the heart of the success of this effort that we've been engaged in, where one group is fixing problems of others, back and forth. It gives you a whole community, a worldwide community, in real time to explore your ideas. So, I'm going to end this here by just kind of summarizing. We have a wide variety of different operational uses. They're closely interlinked, so things that you identify as improvement in our research model become very rapidly available to the operational model and vice versa. But each of these groups has complete control over what gets in by operating by consensus. The operational side of things is able to ensure that the answers don't change, that you can modernize the code without having to go through the whole reforecasting issue that would be required if the answers were changed. So this is something that we think is working very well. It's engaging an increasingly large number of people, but critical to all of this has been this community open development approach, very much in line with the spirit of ACCESS-NRI that Andy laid out in the first talk. So, thank you very much.
David Hutchinson from UNSW. Just wondering if you have any plans to incorporate paleo-cloud applications.
Well, that was the outside NOAA's mission, but there are other places in the MOM6 consortium, in particular NCAR, has paleoclimate as very much a part of their mission. And so that actually brings up one of the things. We all have our mission objectives. Some of the things that we're doing here are going to carry over. So for instance, we're doing a lot of work on improving the ability to forecast the tides. Because we're NOAA, we're interested in tides in the 21st century. That's what the American taxpayers pay us to do. NCAR, on the other hand, has funding from a different channel. Exactly the capabilities that work well for the tides in the 21st century should work well for exploring, say, the tides in the last glacial maximum. Those capabilities become immediately available by the use of this transparent shared code. And so I guess the short answer is, not me personally, but as a collective consortium, absolutely yes.
right, thank you. Kieran?
Thanks. I have a question from the forum from Inistayo. He asks, that's the federal forecast system. UFS is also the ethics setting of compatible requirements. How many does development ethics gets encouraged?
I'm sorry, can you speak up a little bit?
What was the next program? Sorry, that
Just one more time and maybe a little slower.
yeah. Sorry about that. So success of overall forecast system, UFS, seems to hinder all development ethics is saying of how our medium-sized development ethics gets encouraged to change to the development systems of the larger groups. What was that as that program?
Okay, so this is, the question is getting at how was it that everybody was managed to be persuaded to participate with this new UFS paradigm of shared components. Different components had different strategies and was based on the nature of the community. In the case of the atmospheric dynamic core, there was kind of a competitive process that stretched out over several years where it's kind of a downscaling selection that led to the choice of the dynamic core. In the case of the ocean, it really was the community coming together. One of the critical steps about the time that UFS was trying to figure out where to go with the ocean model, NCAR was also trying to figure out to go with their next generation ocean model. And so GFDL was one of the groups where we were asked, would you be interested in NCAR using MOM6? And that was the point where we really established this flat, very open development. I mean, many of you may know that MOM6 has been linked with GFDL going back many decades. What we gave to NCAR and what we give to everybody else is basically the ability to collaborate in this open system with control over their solutions in exactly the way that we have. So it's completely flat. You know, there is no first among equals, it's equals among equals. And that pulled together the NCAR, the HICOM community. We have other parts of NASA that are using MOM6. And so in that case, it was really a bringing together of the US large-scale ocean modeling community, or most of it, on this kind of explicitly equal, transparent basis that managed to pull people together. So there are different approaches for different components. And yes, there are people with small efforts in terms of the number of people. But the thing that we see that open development does in many cases is it gives them an avenue for their small efforts to come in, to contribute. And on the ocean side, that's something that we think has been very successful. It's also been very successful, for instance, on Wave Watch 3. And those are the two components where this open community development aspect is most mature. In other cases, once there was a selection, the Weather Service was able to provide generous funding to encourage people to take what they knew and apply it to the new system. So carrots and sticks in collaboration, or carrots in collaboration and sticks, I guess.
Up in the back.
Thank you so much for your talk. Pat Wolfman from UCF Tasmania. I'm interested in the embedded iceberg you mentioned as one of the features of MOM6. Does that mean the grounded iceberg or the free floating iceberg? Thank you.
Yeah, so I did mention icebergs as one of the features. Alistair Adcroft talked extensively about this at last year's ACCESS workshop. We're actually really excited about where we're going with the icebergs. So this is both point icebergs, but also finite area, large Lagrangian icebergs, big tabular icebergs. And we're doing this as something that's an integral part of BOM. The reason for that is because of the dynamics of icebergs. Icebergs are water, they float, they participate in gravity waves. If I had a bucket of ice and I slosh it back and forth, I can make waves. If I had ice cubes in that, they would move back and forth. They're fundamentally couple dynamics. We're using, we are adapting MOM6 so that the iceberg dynamics, or parts of the ice dynamics, are optionally included in MOM6 to be able to capture that motion. But those icebergs, once they are able to displace water, they can displace enough water to ground. And so we're actually pretty excited that by going back and really thinking about the physics of the different components, not breaking it up by kind of traditional institutional grouping, so you have sea ice people and ocean people, what we really have is the dynamics of the coupled system. And so in this case, incorporating icebergs into the ocean model, revisiting how we're doing the coupled time stepping, we think it's going to open up an awful lot of exciting new possibilities to address new scientific questions, including how icebergs work, including what happens when they ground. What do they do when they're blocking flow, creating polynyas, creating upwellings? And so it's one of the areas that we're really excited about. If you're interested, there's a really nice paper by Alex Huth that came out in GRL a few months ago, January of this year, looking at different modes by which icebergs can break up, and in fact, looking at the breakup of one large iceberg near South Georgia. Part of it was breaking up because it hit the land and the stresses were enough that it broke. Part of it also was it stuck out into a sheared ocean current, and the ocean current sheared it apart. So if you go to the GFDL bibliography, you'll find Alex Huth's paper. It kind of gives you an idea of some of the really exciting things that we think can happen with icebergs, but then are, again, almost immediately made available to people to look at other things using the same tools.